Good evening, ladies and gentlemen, and welcome to the Arvin Gottlieb Planetarium live shows. We know many of you have been watching these programs over the last several months, but I wanted to take a moment to say thank you for your support and bring you up to date on what's happening at your Science City. We've been closed for nearly 8 weeks, and we've had no revenues from our attractions here at Science City and Union Station. But we continue to put all these great programs online. It's becoming challenging. We know you enjoy this program, but I'd ask you tonight to join us in donating and supporting this magnificent facility, but more importantly, the great staff that has been bringing programming into your home, just like Patrick. So tonight, enjoy this program, learn, and take an opportunity to just press that button and make a donation to Union Station and the great team at Science City. Over the next few weeks, enjoy all of the programs that we have at Science City at home. We thank all of our sponsors, and especially tonight, enjoy the programming of the Arvin Gottlieb Planetarium. And we thank our friends at Arvin Gottlieb for investing in bringing this great institution to Kansas City. Now, I know you've enjoyed the several weeks of the programming, but it was all made possible by a dedicated team at Science City and, of course, an outstanding educator that brings the stars to Kansas City. Ladies and gentlemen, please welcome Patrick Hess.
All right, welcome back everyone. Thank you so much, George, for that message and for those kind words. Sorry again for the technical difficulties. We're trying out some new formats here, as you can see. But once again, thanks, George, for chiming in with that message. And big special thanks to our 10,000 member households that help make live events like this possible. As George mentioned, supporting these live online programs is vitally important and really easy. Just click the donate button you see on the Union Station Facebook page. If you're streaming from the Union Station page, you can see that donate button. If you're streaming from the Planetarium or Science City Facebook page, you can just head on over to the Union Station page to find that. We've literally invested millions of dollars in facilities and technology that make all of this possible. And we really can't wait to welcome you back in person, and we really appreciate that you're here with us online today. Every dollar of your support does really make a difference. For now, though, let's jump into our Friday evening live stream. Once again, my name is Patrick Hess. I'm the Planetarium Specialist at Union Station. And I've been coming to you live for the past few weeks, just about a couple months now. And we've been streaming all about space and astronomy. This is our virtual planetarium. I'm coming to you live from the Eagle Nebula right behind me. I'm just kidding. I'm actually in a pocket dimension that is very green colored. But we've been streaming on Mondays, Wednesdays, and Fridays at 6 p.m. and we're going to continue doing that. For those of you who are just tuning in for the first time, just to give you a little overview of how things work. On Mondays, we do a What's Up live stream where I give you a tour of the night sky and I tell you different stars and constellations and show you different things you'll find in our local evening skies, and that'll get you primed for the week for stargazing. Wednesdays is our deep dive live stream. On Wednesdays, I dive into a topic all about astronomy. We've covered a lot of different topics so far. We've talked about things like stellar evolution. We've done a tour of the solar system. I've given you a list of my favorite Messier objects, as well as probes and rovers. You can find recordings of all these live streams on the Union Station Facebook page and all of our other Facebook pages. So if you missed any of those and you're interested in those topics, you can watch those again if you'd like. And we're going to be continuing those Wednesday deep dives into the future. Next Wednesday, we are going to be taking a little different approach than we've done so far. I'm going to be streaming a telescope setup procedure. So I'm going to take my telescope out. We're going to shuffle things around in my pocket dimension here, and I will teach you all about telescopes, how they work, how to set one up. Specifically, the telescope we're going to be setting up is going to be a reflecting telescope with an equatorial mount. Now, a lot of you probably have telescopes lying around in your garages or attics gathering dust. Well, I'd encourage you to take a look at those and dust them off and Even if they're not the exact same type of telescope we'll be setting up, you'll still learn a lot about how telescopes work and some general principles and best practices for using them. So tune in for that. That'll be next Wednesday at 6 p.m. And then Fridays is our Fan Friday, and that's what today is. Today we are going to be answering your fan questions live, so be sure to be leaving them in the comments section of your live stream, whether you're watching on the Union Station page, the Planetarium page, or Science City. I'll be monitoring those questions. And if I miss any, we'll be sure to grab those as well before our stream ends. Speaking of which, I did miss a couple questions on Wednesday. That stream this week, we were taking a dive into rovers and probes, and I had a lot of stuff to cover, which meant I didn't get a chance to answer many questions. So we're just going to touch on some of those questions, and please start leaving your questions today in the comments, and I'll be sure to get to them. But while we're waiting for you guys to gather your questions and to start tuning in, let's answer some of these questions from last time. A lot of these are about probes. Eric asked last time about where probes were launched from, and I talked about a number of different probes from a number of different space agencies. Now, a lot of the probes in the early days of the space race were launched by both the United States and Soviet Union, so those launch sites were in those respective countries. You know, a lot of our manned missions were launched from Cape Canaveral, but not all satellites are launched from that location. There are a number of different locations around the country where we launch our satellites. That location is really good, though, because it's very far south, and when you're launching something into space, you want to be close to the equator, and that just makes it easier to get to space. We had a question from Maddie last time. We were talking about Titan and Saturn, and specifically the Cassini probe that explored Saturn. And Cassini carried with it a lander named Huygens, and that lander landed on the surface of Saturn's largest moon, Titan. In fact, let's go over to Titan. I've got our view of Saturn here from last time, so let's go ahead and fly on over to Titan. Titan is a very cloudy moon. Luckily, we can turn the clouds off in Space Engine here. If you missed it during our live stream last time or our solar system tour, Titan is the only other body in our solar system that has oceans of liquid on its surface. This isn't liquid water, though. This is liquid methane. But Maddie specifically asked, how do they pick a spot to land? Or do they pick a spot, or do they just hope for the best for those probes? And usually scientists and rocket scientists will try to pick a good spot, and they'll try to be precise about where they were going to land. And that, you know, even the manned missions don't always land in the exact right spot. Apollo 11 landed quite a ways away from its intended landing site. But then after that, the later Apollo missions landed pretty close to where they were aiming for. But I did a little research specifically for Huygens, and I found a little bit of information. And for Huygens, they were looking for a specific landing site, and there were a couple factors that led them to picking. So there were a couple of different considerations for the Huygens probe, or where it was going to land on Titan. You know, a big consideration was sunlight. You know, this probe was going to have solar power, so they wanted it to be in just the right latitude. In this case, 80 degrees latitude or longitude, and 24 degrees south, so lying between a certain latitude, basically, so that it would get sunlight for as long as possible, as well as elevation, so that it would be wouldn't be disrupted as much by the layers of the atmosphere. So there are a couple of considerations about that, and that is what led them to pick a landing site for Huygens. As to how close Huygens got to its intended landing site, I'm not 100% sure. I unfortunately could not get a precise answer to that, but hopefully that gives you kind of a framework, Maddie. Kristen asked about when the Dragon was going to launch. That's a fun question. I'm guessing Kristen was asking specifically about the Crew Dragon space capsule. This has been in the news, and I've talked about this a couple times, but it's worth repeating. This month, on May 27th, NASA will launch American astronauts from American soil for the first time in nearly a decade, since the shuttle program ended in 2011. And they will be flying aboard the Crew Dragon space capsule from SpaceX. So May 27th is the launch date, and I believe that launch will be happening at about 3 p.m. We'll be posting links to live streams of that launch, and then of course on Wednesday, our deep dive live stream, that day will be all about SpaceX and space exploration by people other than NASA, so private space industry, basically. So May 27th, mark your calendars. And Tammy asked last time, do we know how long it took to build the first probe compared to the most recent ones? And that's a really great question, and I'm glad you brought that up. So to answer that question, it's Friday, everyone. Sorry for some of the technical difficulties. To answer that question about probes, well, I think that is a great question. And, you know, I think answering that question gives you sort of a peek into you know, the different eras in space exploration. During the early days of space exploration, especially during the space race, there was a lot of pressure, and a lot of, not only a lot of pressure from, you know, other countries. Obviously the United States and Soviet Union at that time were racing to get to space first, whether to send a probe first or send a person first or get to the moon first. But there were a lot of political considerations and political influences during that time too. So during the space race, a lot of our national resources were dedicated to space exploration. In fact, a lot more than you might imagine. So back then, I believe it's around 3 to 4% of the national budget during the bulk of the space race was dedicated to NASA. Now, to put that into perspective, today we do not spend nearly as much on space exploration or NASA. And this is a common misconception, actually. There have been studies actually polling just regular people, asking them how much they thought we spend on space exploration as a country. And a lot of people think we'd spend upwards of 10 or even 20% of the national budget on that. And that's not true at all. In fact, today, NASA gets about less than 0.5% of the national budget. And that's all the spending money that the United States government spends on anything throughout the year. So it's pretty miraculous that what NASA can accomplish with such a small budget. But because of that, during the space race, things happened really quickly because there was a lot of pressure and a lot of resources behind it. You know, you can look at the main Apollo missions, and those were sometimes months apart from one another. And it's crazy to think that, you know, Apollo 11 came back, and then within a couple months we sent another Saturn V rocket, which was already prepared, ready to go into space. And it was similar for the space probes like Sputnik and other unmanned missions. But to contrast that with today, obviously a lot less of a resources are put towards space exploration, but things take a little bit longer. And they also take longer because there are a lot more scientific people involved, and a lot of these deep space explorations are more scientific and less political. But to give an example, the Hubble Space Telescope, which has been in space for 30 years now, we just celebrated its anniversary actually a couple days ago, or a week or so ago. Its successor is named the James Webb Space Telescope. You may have heard of it over the years. It's currently under construction, and it's planned to be launched next year. Now, this planned launch date has moved and been pushed back a couple years as things shift and as the development time gets extended. But the James Webb Space Telescope program was started in 1996. So 24 years that space probe has taken, and it hasn't even got to space yet. So just to give you an idea of these of the difference, you know, things take a little bit longer these days. But there are more space agencies involved, like the European Space Agency in Japan and modern-day Russia. So there may be more probes and satellites into space these days, but in terms of these deep space probes and a lot of these NASA projects, they take quite a bit longer. I think that is all the questions we had last time. We had a lot of people commenting about the Golden Record. I talked about the Golden Record, which is a message that we attach to the Voyager space probes, a message to possible alien civilizations. And there's a lot of interest, it seems like, from a few folks, like Maddie, Tracy, and Karen. And I think some other people who would like to learn all about the Golden Record. So I'm thinking probably I'll move it into my schedule for the next few weeks. Maybe a month or so from now, I'll do a deep dive on a Wednesday all about the Golden Record. So we can add that to our calendar since there seems to be some interest there. All right, so I'm gonna head on over to the comment section and let's see if anybody's watching or if I'm speaking to the void. I'm going to start with the Planetarium Facebook page. If you are not subscribed to the Planetarium, be sure to like and subscribe so you can get all the space updates that we post on the Arvin Gottlieb Planetarium Facebook page. Eric asked, do we think that the moon was once part of the Earth? And we do. In fact, to answer that question, I'm going to load up another application. Let's go ahead and get that started. So we're going to be using something called Universe Sandbox to answer that question. And where is it? It's somewhere around here. I'm going to vamp. All right, there we go. So let's go ahead and start up Universe Sandbox, and I'll start answering that question. So the question again was the moon part of the Earth? So there are a lot of theories for how the moon was formed, and one of the main theories is that it was once part of the Earth, and basically a few billion years ago, a massive chunk of rock the size of Mars, sort of a protoplanet, crashed into the Earth and kicked up a bunch of debris that got sent out into space, that debris eventually coalesced to form the moon. And so with Universe Sandbox, we'll actually be able to simulate this. And so we're going to get it loaded up. It might take a minute to load. It's loading now. All right. So Universe Sandbox is a program where you can experiment with physics simulations and do all sorts of sort of what-if scenarios with the universe. Oop. Still getting used to some of these new controls. Again, it's Friday. All right, so here we go. So right now we've got a simulation of our solar system loaded up, but Universe Sandbox is really cool. It has a bunch of simulations already pre-programmed, and let's go ahead and pick that up. So we want a Earth and Mars collision. So we're going to load up the simulation pause. So this is simulating what could have happened billions of years ago when an object the size of Mars did crash into the Earth. And actually what we want to do, I'm going to do something else here. Let's delete Mars. Oop. There we go. And then you can add objects here. So we want to add Mars, but we want to launch Mars at the Earth. I'm going to launch it sort of on the side here. Actually, let's go ahead and start time. Oop. All right, so we're going to launch Mars at Earth. And let's see what happens. So when Mars crashes into the Earth, it's going to kick up a lot of debris, and that debris is going to get flung out into space. And some of that debris will crash back down, but a lot of the debris will end up orbiting the Earth. So what ends up happening basically is this debris will sort of be floating around, and over millions of more years, these chunks of Earth debris will coalesce again to form a moon. So that's kind of the main theory for how our moon was formed. And with Universe Sandbox, you can play around with other simulations like this. Deborah says hi. Hello. All right. So just a reminder that if you're looking for that donate button, you can find that if you're streaming from the Union Station Facebook page. We are live streaming this live on Union Station, the Planetarium, and Science City. And there's also a link in the comments there. Caleb wants to know, what are the astronauts studying in the Dragon mission? Oh, that's a good question, actually. The one that I don't know the answer to. So let's look. So this is the first personed mission of the Crew Dragon capsule. More than likely, most of the plan of this mission is just testing the capsule, and they may not be planning on staying there for very long. All right. So we're looking for the first Crew Dragon mission. So we've flown the capsule without people in it before, but we've not yet flown it with people in it. So, all right, so here it is. Crew Dragon Demo 2 is the official name. And so this mission is going to, well, apparently it's going to last between 30 and 119 days. So that information might be slightly off. That seems like quite a range. Yeah, so they're just testing out, the docking procedures of this new capsule. And, those particular astronauts are pilots, and they're not going to be going up there to do a lot of science, most likely. But we'll see. They may not have announced much more about that. But there is a full mission planned for August of this year that'll actually send 4 astronauts aboard the Crew Dragon, and these astronauts will be going there to do, do their regular science job, basically. So that'll be the main sort of science mission. All right, so let's pop on over to the Union Station page and let's see who's chiming in. Christian's bringing up a fun fact that the video game Tetris was the first video game to launch into space. That sounds plausible. Oh, so we got a question from, looks like Hanny from, Eleanor, rather. Eleanor is asking about the Starlink satellites. So these have been on the news recently. In fact, somebody, I think it was Gary Lezak, tweeted about that a couple days ago, that he saw a line of dots going across the sky and he was wondering what it is. The Starlink program is going to be a satellite constellation. So the plan is actually to send a lot of these satellites up into space. They're relatively small communication satellites. And the plan is to send over 1,000 of them, and actually 400 have already been sent into space. And the main mission of Starlink, which is a mission by SpaceX, this is a program that they've created and they've built these satellites. Their mission is to send a network of over 1,000 satellites into space to bring internet to parts of the world that don't have access to that. Now, there has been some controversy because these Starlink satellites have been fairly bright, and over time SpaceX has redesigned them and changed their paint to make them a little less shiny, reducing their albedo. That's the sciencey name for shininess. But there's been a lot of concern in the astronomy community because with 1,000 of these satellites in the sky, satellites that you can see very brightly, and that's what people have been reporting. They've been reporting a line of very bright dots moving across the sky all together, and those are the Starlink satellites. Now, the ones that are that bright have likely not reached their orbital height yet. They're very bright because they're relatively close to the Earth, but they're going to be farther away. So they'll be a little bit dimmer by the time they reach their intended altitude. But again, there is concern from the astronomy community that all these extra lights in the sky will disrupt astronomical observations. And I'm not going to profess a specific opinion about this. I'd encourage you to read up about these satellites and the astronomy related to them and decide to yourself. But if you do notice a line of bright dots moving steadily across the sky that aren't blinking, there's a good chance that those are a recent Starlink launch. Okay, Luke is asking why the gravity is different on every planet. And that's a good question. And, well, I'd answer it by first saying that gravity is not really different on different planets. Gravity is the same everywhere in the universe. Gravity is just the way we describe the force that pulls objects together based on their mass. Now, different planets exhibit different amounts of gravitational force, and that is all due to their mass. So the larger an object, the more mass of the object, the more gravitational pull it has. So that's mainly it. It all has to do with their mass, not necessarily their size, because a planet could be very large but have a very low density like Saturn. It's all about their weight, so to speak, their mass, so how much matter is in them. And everything in the universe is affected by gravity, even light. You can see simulations of black holes. Now we can visit a black hole with our stream here. Let's go to Sagittarius A star, which is the black hole at the center of our galaxy. Black holes are incredibly massive objects, and they're so massive that light cannot escape their grasp. And I have to turn the brightness way, way down so we can see it. But as we zoom in on this, we can see that it bends starlight around it, causing this warped view. But this doesn't only happen around black holes. The sun actually causes this same gravitational lensing. We can actually see that during a total solar eclipse. Some astronomers take pictures of stars near the sun during that eclipse, and they observe them to be slightly out of place. That's actually one of the ways we've proven that these theories of gravity do exist. So it's all about mass, basically. And even a person has gravity, but since we're on Earth near an object that has a lot greater mass, we're not as affected, or we don't exhibit our own gravitational pull on anything else. But there are very, very tiny asteroids out in space that are just a mile across, but even have their own gravity. We've sent probes. I talked about one of these probes actually on the last stream. We've sent probes to these small asteroids, and now they will be able to orbit them and be able to land and be pulled to them, but they won't have quite as much gravity. That's why if you've seen either in fiction or videos in real life of astronauts walking on the moon, they appear to jump a lot higher because the moon has less of a gravitational pull on them. So they're able to jump a lot higher, and they, in a sense, weigh less than they do on the Earth. Great question, Luke. All right. Let's see. Looks like I may have answered all the questions so far. Again, if you've got any questions, throw those up in the comments below. In the meantime, though, let's go back over to Universe Sandbox. And let's try out some other simulations. Let's see if there's anything interesting. These are all about the Earth. Let's go with... we can go with some historical simulations. So one probe I didn't talk about last time is a probe that was kind of famous recently. It's called the Parker Solar Probe, and this probe, its mission was to get really close to the sun. And this probe actually broke a speed record. It became the fastest probe ever, and we can see its speed shooting around the sun here. So it had a very elliptical orbit, or it has a very elliptical orbit. It's making multiple passes here. Yeah, so this is actually a simulation a little bit in the future. It's going to make this particular pass in 2024, but it has already been getting close to the sun and been breaking speed records. It's going to orbit the sun 24 times, and it's already made a couple orbits. Now, orbits like this are interesting, and I can speed up time a lot more here. And one thing we can see in Universe Sandbox is that we can see that the solar probe gets very slow at the end of its orbit before it kind of slingshots around the sun. So you can see it gets really fast when it gets close, and it slows down as it gets farther away. And all orbiting objects behave in this way. Just checking to see if we had any other comments. Got a question from Eleanor. How close do you have to be to a black hole for it to absorb you? That's a good question. Let's go back to our black hole over here. So black holes have different parts to their structures. So if we zoom out here, we can see that this particular black hole has a lot going on. Without lowering the brightness, we can see two very bright things. We can see this ring of particles. This is called an accretion disk. And this ring of particles is various gases and other particles that are getting close to the black hole and accelerating really quickly. And as they accelerate, they get really, really hot and they light up. And then sometimes particles will get ejected, and that's what these streams are on either side of the black hole. Streams of particles being ejected at near the speed of light. But these particles are getting close to the black hole, but not getting sucked in. In fact, there are actually stars that are orbiting the black hole. Quite a few of them that we measured here. And you can see that these stars are getting pretty close to the black hole, but they're not getting sucked into it. So it seems like you can get close to a black hole, but not really be affected by anything, right? It's kind of weird. Well, we can go back to Universe Sandbox, and we can experiment with that. We can load up a black hole. First, I'm going to load up just a simple solar system model. So here's our solar system. And if I press play here, we can see all the planets orbiting in their known pathways. Now, what if I paused time, and what if I replaced the sun with a black hole, the same mass as the sun? So this this black hole is not going to be any bigger or smaller than the sun. It's just going to be the exact same size as the sun. So we're going to replace it with a black hole with 1 solar mass. So I'm going to replace it, and I'm going to press play again, and you'll notice that nothing changed in our solar system. All of the planets in our solar system are still orbiting around the sun. Now, our solar system would get pretty dark if this were to happen. We actually wouldn't notice until about 8 minutes after the sun turned into a black hole, because it takes light 8 minutes to travel from the sun to the Earth. But as you can see, nothing really changes when the sun is turned into a black hole if it's the exact same mass. The only weird thing that happens around black holes is if you get really, really close to them. So if we zoom back into Sagittarius A star, which is a black hole at the center of our galaxy, we'll see a very dark spot, and this is called the event horizon. This is the point of no return for this black hole. If you can get really close to this point, but you won't fall in. You might accelerate and then get flung back out into space, but if you get beyond this point, the event horizon, then there is no return. Then, well, we really don't know what happens, honestly. Our science sort of breaks down when we try to imagine and study what could happen when we get this close to a black hole. We just know that nothing can escape as far as we know. Whee! And now our stream is stuck inside the black hole. Kristen asked, what will it look like when the Andromeda Galaxy collides with ours? Well, a Universe Sandbox actually has another simulation that'll help us to understand that. So this has some galaxy simulations. So let's load up some simulations of our 2 galaxies. And this is going to simulate what happens as they collide. Now, the Andromeda Galaxy and the Milky Way are heading towards each other at about 86 miles per second. 68 miles per second, I believe. Which is pretty fast, but they're still so far away that it's going to take about 4 billion years for them to reach each other. Now, what we'll see in this simulation is our 2 galaxies colliding and merging, and it will look kind of violent. So if I speed up time again here, we can see when our 2 galaxies get close to each other, they will kind of be absorbed in one another, and some stars will get flung way out into deep space. And the structures of our galaxies will be totally destroyed. And eventually, over enough time, our 2 galaxies will combine once again to form a new galaxy. Now, fortunately for us humans, we don't have to worry about this. Most stars are so far away from one another that there is very little chance of any 2 stars actually colliding with one another, or even getting close enough to mess with each other's solar systems. So all we would see is the Andromeda Galaxy getting closer and closer to us and slowly getting brighter and brighter. So it'll be quite a light show, but again, it won't actually hurt anybody who happen to still be around. Now, I should mention that the Earth may not be around by then because our sun is progressively getting hotter, and in about 1 billion years, the Earth will likely not be habitable anymore. But by then, maybe humans will have started to live on other planets or in other solar systems, and maybe we'd be able to see that galactic collision. We actually do have photos of other galaxies which have collided with one another. Let me pull up one of those for you. So here is a couple of pictures of galaxies that have already collided. So this photo was taken by the Hubble Space Telescope. And this is, let me double check which particular galaxies these are. No, it's not telling me. Let me find a better picture. All right, yeah, here we go. This is what we want. So here's a photo of 2 spiral galaxies colliding. These are galaxies NGC 2207 and IC 2163. Very exciting names. So here is a picture of 2 galaxies colliding. So if you were out in deep space and looking at the Andromeda Galaxy and the Milky Way as they collided, you might see this. Now, one interesting thing is that our galaxies, when you look at photos of the Milky Way in our skies, or the Andromeda far away, it's a lot more blue in color, and that signifies that our galaxies are relatively younger. Well, these galaxies are a bit older, and their yellow color tells us that because the wavelengths of light coming from their stars indicate that the stars overall are a bit older. But this is an actual photograph of other galaxies colliding, so we know this happens, and we've seen the results of this. Now, what will happen after our galaxies finish colliding is they'll become an elliptical galaxy, which really won't have the nice spirally structure of the Milky Way. It'll look sort of more blobby. This is M87, which I believe is the galaxy that we took the picture of the black hole of. Yeah, so here's M87, which is an elliptical galaxy. It's just like our galaxies. It's full of stars, but it is not spiral in shape, and it doesn't have those nebulous clouds that we can see. So its stars are a lot older, and all those star-forming regions have since finished making stars. Michelle's saying that this is the coolest thing. Thanks, Michelle. I'm glad you are enjoying this. All right, any other questions? Let's go over to looking at the Planetarium page. Science City. Looks like I might have gotten all the questions that people have asked so far. This is your last chance, folks. If you got any questions for us before the end of this week, go ahead and drop them in the comments, and I'll be sure to answer them. Let's see if there are any other fun things here. Let's go back to Space Engine. And back to Planet Earth. Oop, very dark. There it is. We're in the future. There's the current Earth. Okay, well, it looks like I've answered all of your questions for today. So if there are no more questions, then I guess this brings us to the end of our live stream today. So thank you all so much for your amazing questions, and to everyone else, thanks for joining us for this fun exchange today. Don't forget, folks, that to help keep these types of experiences going, we do really need your help. If you're a member, be sure to renew your membership, and if you're not a member, feel free to join and become a part of our family. If you haven't found that donate button on your screen, please look now, and you can find it and I'd encourage you to think about donating to help keep this type of programming coming to you. Your direct support makes a really big difference for us. And finally, please tell your friends about these online events. We'd love to involve everyone as possible, and I love it when there are more questions for me to answer than I have time to answer. Yeah, tell your friends, tell them to tune in for our Monday streams where we take a tour of the night sky, our Wednesday streams where we take a deep dive to an astronomy topic, and Friday where we just answer your questions and just kind of hang out. It's a lot of fun, and if they don't check out our live streams, or if you have been checking our live streams, be sure to remember to buy a Planetarium ticket when we do finally reopen, and you can see me under the stars of the Planetarium. For now, though, let's stay connected, and we look forward to seeing you all here again, this time on Monday at 6 p.m. live streaming from Union Station, the Planetarium, and Science City. Don't forget, Wednesday's stream will be all about telescopes, where we will be learning how to put one together and learn some best practices for using them. For now, though, I have been Patrick Hess, your Planetarium specialist. Thank you all again so much for joining us. Oh, I did notice one more question come in, so we're just going to answer that. Olivia, if you're still watching, Olivia wanted to know what would happen if the Earth collided with Jupiter, and that's a very fun thought. So we're gonna leave our stream with just a very happy image of Jupiter and Earth colliding. I believe there's a simulation for this already. So let's just go ahead and load up. Let's load up. Well, we'll just load up the solar system once again, and let's zoom in on Jupiter. Woo! There is Jupiter. All right, and we'll just go ahead and launch the planet at Jupiter. The Earth. This is very cathartic. This seems like a fun Friday thing to do. So let's just... whoop, that was a little bit too fast. Let's slow things down a little bit. We're going to launch another Earth at Jupiter. And, well, Jupiter's a lot bigger than the Earth, so it would just kind of gobble us up. So imagine that when you're eating dinner tonight. Imagine you're Jupiter eating the Earth. So thanks for that very weird question, Olivia. Love weird questions, especially when they have weird answers. Yeah, thanks again, everyone, for tuning in. And if I missed any other questions, we will pick them up next week. But for now, I hope you all have a wonderful evening. Bye-bye.